That's great, Barb. Thank you so much for that introduction.
Oh,
It
you're
is such a
welcome.
pleasure to be able to talk to you this evening about the microbit. So
Okay.
England was like one of the first countries to have the microbit. It was a BBC project back in those days, and this was rolled out across the country. One of these lovely things was put into the hands of every 11-year-old. You can imagine what's going to happen with that. A lot of them just end up in school cupboards that the schools don't hand them over. The ones that do get sent home, I do worry about how many of those actually got used. It was a wonderful idea in principle, but in practice, it seems so much more practical to do this in school. Yes, it's lovely when children go take the microbit and go and make something amazing with it, but think about ways of integrating that into the curriculum. As Barb mentioned, we put computing onto the national curriculum as part of the panel that drafted that. Here's the text that we came up with. I'm just checking that the screen share works. So there's a lot here about cool practical programming. Key stage 3 is 11 to 14-year-olds. So this is the target age range, at least in English terms, for the microbit. And so, there is lots of stuff that you could do with the microbit. You get then these weird bits going in there about what is this? Understand simple Boolean logic, for example, and or a not, and some of its uses in circuits and programming. And you've got to wonder, is that really the sort of thing I want every 14-year-old to have an understanding of? Maybe. Understand how numbers can be represented in binary and be able to carry out simple operations on binary numbers. Isn't this exciting? Okay. And this tends to get taught in a very theoretical, almost like a maths lesson sort of way of just working with converting numbers from one base to another. And I think there is a tremendous synergy here between that lovely box of the microbit somewhere in the computing lab cupboard and the requirement to teach this stuff, which could come across as really quite dull. So let's have a go at seeing how we might get on with that. So I'm going to clear the screen to start off with. So let's just pop that into my start loop. And then let's have something happen when, I don't know, button A gets pressed. I'm just going to write some code here, and then I'll just pause for a moment and see if people can figure out what this is going to do. Let's create a variable. I'm going to call this X because I once did a maths degree and we always were trying to find X. So let's set X up, not to be the intuitively obvious 0 there, but let's go with a 4 to start off with. And what we're going to have going on here is a little loopy thing while the LED, LED at point X, I'm going to go for 4 again. Whilst that's lit, do something. In fact, specifically, turn that little LED off. So variable X again, let's pop the 4 in there. And then the very last, we've got to keep it decreasing X whilst we're doing this. So let's change X by -1. And then finally, when we get to the end there, let us plot the very last of those. So plot whatever X has got up to. And again, using 4. So here's a moment, folks, okay? We're supposed to, or one of the pedagogies that we're encouraged to adopt now in English schools is this idea of read the code before you run the code. So if I was teaching this with a class, I'd say, okay, here's this weird program. Is there anybody here who can predict what it can do? I can't see anybody putting their hand up, but you could type into the chat there. Okay. Anybody, any ideas what this is going to do if we run this? Nick and Pauline and Rachel, it's lovely to have you here. It really is. Yeah, this often happens with these video lessons. Nobody types in. Okay, so once we've made a prediction, we get to run the code. And I'm hoping I've not made any mistakes in here. Let's see what it does. Click button A. And a little LED comes on. How exciting is that? Let's click button A again. Oh, and another one's come on. Actually, that one went off. And now I've got 2 of them on. Okay, that was like 3 of them on. Okay, so thank you, Rachel. Move a dot down, not so much. Move a dot across, Nick. But you should, I hope. Let me reboot the thing. Recognize this pattern here. 1, 1, 0, 1, 1, 1, 0, 0, 101, 110, 111, and 1000. So we have now a binary counter as if by magic. And, pausing for a moment or two, figuring out how this magical code works is quite fun. I'm only able to count up to 31 with this. I guess we could go on. I have, however, got 5 rows on my lovely microbit screen here. So why not add in a few more rows of this? So let's pop another variable up here. Make another variable. I'm going to call this y. Why, you might say? Well, and we're going to set y up as 4. Oops, not 5, 4 at this point. And this time, let's have that y in there, and in there, and in there. Okay, and this time when we get over to the left-hand column, when x hits 0 there, first column is column 0, we're going to need to do something. So I've got a little logical test going on here. If something happens to be the case, let's do a little comparison here. If variable x actually is less than 0, because we have got a column 0. But once it gets to less than 0, then let's reboot x to over onto the right-hand side there with column 4. And let's change y this time by, again, -1 to move up the screen. Fingers crossed, folks, a moment of truth. Okay, so we get to... that's 16, 24, 31. What's going to happen now? Yes! And I move into the next row of the screen there. And there's a little exercise for the reader there as to how big a number could you display on screen? Hey, Google, what's 2 to the power 25? Okay, so somewhere in the region of 33 million. I've got a counter here, which would count like half the population of the country. Sorry, Nick. Okay, if we wanted to do that. Now, this counter thing is moderately useful. So during the whole lockdown-y thing that we had here, there was people at the entrance to supermarkets carefully counting the number of people who went into the supermarket using technology no more advanced than this sort of device here. And you kind of want to keep track of the people leaving the supermarket, because people sooner or later left the supermarket as well. So do we want another button here, 2 input things, which would actually count down? So if I were to press button B, I want this to count down. What am I going to have to change here to make it decrease? Okay, yes, Rachel, I do more Waitrose than the nightclub, but there you go. Okay, well, probably it's just the opposite of what we've got going on here at the moment. So let's take that plot out. Let's take this unplot out and swap those over. Okay, and that's looking good. It's not quite the opposite, because I had whilst the point was lit, and this time I probably want, if I'm doing the opposite, I want whilst the point is not lit. So I've got a little not operator here. There's my first bit of Boolean logic coming in, whilst not that point. So button A increases, people coming into the nightclub for Rachel, or supermarket for me. There's 15 of them, 8 and 4 and 2 and 1. And then button B, that's down to 14, 13, 12. And, the supermarket is emptying because there was nothing on the shelves at this point. Okay, so we've got a binary counter there. I'm sort of vaguely keeping track of the time. That's about 10 minutes in, and we've got to the point of binary counter. I think that's a fabulous thing for year 7 to do. Sorry, our 11-year-olds. They're supposed to be working with binary. They're supposed to be programming. But there's a lovely way here, I think, of linking the two together. Over on our national curriculum, we have this idea of convert between binary and denary. And of course, if they're going to do the exam in this at the age of 16, they've got to have the hand-cranked method, because our exam in computing, they're not allowed to use a computer. Just pausing for a moment whilst the international audience marvel at that. Don't get me started. Don't get me started. Let's think about how we could actually convert this number, which, we've not stored this number. We've not been counting up. Can we just take the number on the display here and figure out some way of converting that into base 10, or denary, as our exam boards here seem to insist on calling it. Let's have a go at this. So let's just, another input condition. Let's have, oh, not that's the button thing. Let's have, when we shake the microbit, can we get the denary number on the display? How am I going to do that? I'm going to keep track of the place value of the column I'm in. I'm going to keep track of the total so far. So I'm going to create another couple of variables here, one of which I'm going to call place value, not palace value, place value, and the total so far. Okay. And initially, we're going to want both of those to be set to 0. So set the total to 0 and set the place value not to 0. The first place, that bottom left pixel on my screen here, is worth 1 unit. And we're just going to go across the screen here. So we don't know quite how many pixels are lit. So I think we've got to go through pretty much all of them here. So let's start at the bottom right-hand corner. So let's set that x coordinate to be 4. Let's set the y coordinate to be 4. And just keep going, basically. So we've got a while loop going on here. So while I'm doing a comparison. So whilst the y coordinate is somewhere on the screen, so whilst the y coordinate is greater than or equal to 0, keep doing the following. So have a look at the current pixel, and then if that's lit, increase the total by its place value. That seems reasonably straightforward, doesn't it? So what we've got to do here, little logic thing going on, if the LED at, sorry, you love the way I'm narrating this, I can tell, X and Y. If that point is lit, then change the total by not just 1, but whatever the current place value variable holds. So place value of 1, let's just move that out of the way for you. That seems to be okay. What are we going to do next? We are going to increase the x coordinate. So change x to move on to the next pixel, which is over to the left. So that's by -1, annoyingly. Thank you, Bob. Okay, so change the x value by -1, and we've got to update the place value to the new one. So change the place value to be double the current place value. In other words, just add the place value onto the current place value. Then you've got to worry about that thing about moving on to the next row of the screen here, which we did before as a little if-then thing. I can probably just copy my code here, duplicate that, pop that in there. If x is over to the left-hand side of the screen, then reset it to the right and move up a row. That looks as though it's going to be okay. Nothing would happen, annoyingly. So I do actually, at this point, when I finish looking at all of the possible pixels that are on the screen, all possible, up to 33 million of the things, I would actually quite like to see what total I've got up to here. Okay. This is the interesting moment whilst I just check the chat in case anybody has spotted a mistake in my code. Let's see how we get on. So clicking button A, we've seen this bit before, at least it's not broken, which is a relief. And let's shake, oh, let's do a prediction first. This is an 8 and a 4 and a 1. I make that 13 in old money. 1, 3, yes! Okay, it worked. I shouldn't sound quite so surprised, should I? Oh no, but my whole display has disappeared then. Oh God, I've got to go back to 13. This is going to be annoying for the people at Sainsbury's or Waitrose or wherever, the supermarket of your choice. Okay, sorry, little local reference here. Thank you, Rachel. How can we get it back on screen? Well, there are a couple of ways here. I'm conscious of the passage of time, so let's do the easy method, which is just to imagine ourselves pressing that button after we've shown the number. So let's give ourselves a little pause for thought, or the microbit a pause for thought. How long do you think it needs to think? Just a second. All right, and then we're just going to go back and set the total up there. So what I need here is a little repeating loop. For loop coming up next. For index from the range 0 to total, just do all of that stuff I did previously when I pressed button A, but rather than doing that by hand, let's make the dumb machine do all of that for us, automating the boring stuff. That's what we're kind of doing here. There is a deliberate mistake in the code at this point. Glancing over to the chat. You didn't know there would be a test, Pauline. And, there's a lovely teachable moment here about, let's run the thing. What's the worst that could happen? Well, okay, it's a microbit. What is the worst that could happen? Rebooting, pressing button A. Let's pop something semi-random up on screen. And I've got, oh no, I've got an 8 and a 4 and a 2. I make that 14. So if I shake the thing, 1, 4, yes. And then wait a second. Oh, but it's put 15 back on screen. That's not very much fun, is it? Okay, the off by 1 error is the thing here. I'm actually counting up 1 too many thing here. So we need to do a little bit of math. Where have they missed out the S? They've missed out the S here, where we're going to take that total and just deduct 1 from it. And let's pop that back into the thing. Let's run the thing. Okay, popping up a semi-random number on screen. Let's try and get it up into that second row just to check that that works. This is watching Miles clicking his mouse pad. Okay, so I've got a 32 and a 4 and a 1. Is that 37 in old money? 37. Waiting a second. And it has. That seemed to be longer than a second, didn't it? Put that back on screen. So I'm reasonably content now that I've covered quite a bit of the English curriculum at this level. Some of its use, and so understand how numbers can be represented in binary, able to carry out some, example binary addition, conversion between binary and decimal. I've done that bit. Get it? At least. Okay. What next? Well, there is this whole thing there about Boolean. Oh, sorry. Pauline was saying that she was trying to follow and wasn't able to get there. Let's see what happens if I publish the project. Okay, I'm going to copy that code in and paste that in. And with a little bit of luck, you get a working version of this by clicking on the link. I'm not quite sure how that ever works, but see what happens. What's the worst that could happen? Okay, so let's move on to the Boolean logic thing here. I'm not going to worry too much about my shake instruction. I'm also going to, for simplicity's sake, take out that sophistication of having numbers up to 33 million and just have that top row of this. So if I take out that whole moving up a row business from here, I should just be working with that, the bottom row of the display. I'm actually going to pop the A button onto the top row of the display and the B button onto the second row of the display. So let's just have a quick look that that's working as it should be. Oops, oh, I think I may have shook it by mistake there. Okay, let's just get rid of that whole on shape thing. Set button A, set button B. Okay, and button A. I've broken something in the process. Okay, set Y to be 4. Okay, I'm looking at the wrong row. Okay, so Y is 0. That's the top row, and that's 4. This is 1, and that's 4. This is the joys of live coding, live demo. Okay, fingers crossed. Okay, so top row is working on button A. Next row down is not working on button B at the moment because I did it differently. Duplicate this. So there we go. Button B is supposed to do this. That looks like duplicate code, except we're going to work on row 1 for button B. That's looking better. Okay, this is just so you can tell that it's a live performance rather than a recording that I'm playing with you. Okay, playing to you. So we've got button A and button B working. Now let's have a go at doing some Boolean logic with this. I love the fact that the current version of MakeCode lets me create my own functions. I was bemoaning that in previous generations of this. So let's create a function here. I'm going to call this bitwise because I'm going to be doing bitwise operations. And what I'm going to do here is look at both rows of the display there and compute something bitwise on the basis of those. So again, we're going to use our x variable to track how far across the screen we are. So let's set x up to be that right-hand row, which is row 4. We are then going to go across one row at a time and create something on the bottom row here. So we will do an if-then else statement. Oh, let's do the loop thing. While logic, the x variable is greater than or equal to 0, we're going to look at 1 pixel at a time and then plot things. So as I say, logic, if, and we're going to, let's start with doing an OR gate here. So I'm going to pop in a little OR statement for that first Boolean operator. If my LED point or another LED point. Okay, so what have we got going on? If point x0 or point x1 are lit, then I'd like the bottom point to be lit. So let's try plotting point x4. If they're not, or if either, if A is not lit or B is not, oh, if it's not true that A or B is lit, oh, the language is difficult, isn't it? Let's unplot point x, comma 4. Okay, so with a little bit of luck, I've got my bitwise function here. I'm not actually calling bitwise at all, but the point of putting that into a function was that I can call that whether I press button A, or I can call that function whether if I press button B. So button A and button B should count up, and then call bitwise. If either the top row or the next row is lit in a particular column, then we light the bottom row. That's what it's supposed to do. Okay, and there's a problem here, isn't there? Because I'm not changing the value of x. Then change x by -1. Okay, so A is still working, B is working, and look at that bottom row. If there's something lit in either the top or the bottom row, or sorry, first or second row, then the bottom row gets lit. And that's how a bitwise OR should work. So by this point, your, I don't know, 12-year-old should be able to answer the question, hey, what is 6 or 9? And confidently give the answer 15 at that point, because 6 or 9 is 15. That's what the microbit says it is. So we've done OR. And with the click of a mouse here, I can swap this over to a bitwise and this is the one that really freaks out their friends in the playground. Well, the geeky one's friends in the playground. There's 7 coming on there. And that's 3. What's 7 or 3? No, 7 and 3. And the answer is, of course, 3. 7 and 4, 4. So we can, 7 was not a particularly good example there. There we go. So what is, I think that's going to be 10 and 8. 10 and 8 is clearly 8 because that's what the bitwise operation says it is. So we're doing pretty well. We've got binary, we've got binary denary conversion. We've started to play with logic gates on a bitwise basis here. Not through storing the numbers, but through actually manipulating bits pretty much directly themselves. Let's go on and see if we can make an XOR gate. Now, XOR is trickier, okay, because exclusive OR, we've not got quite the same facilities. So, Barb, can you remind me when I'm supposed to finish this session? I think it's 7:40 or 20 to the hour. Okay. Yeah.
So you maybe come back on. Yes, you're right.
Okay, that's fine. Okay. Bless you, Pauline.
Here I was
Let's
over
press
there
on.
doing
Let's
my
press
work.
on. Let's see how far we can get with this. Let's have a go at creating a new function this time, because annoyingly, here's a bid to the Microbit Foundation, folks. How come and or other logic gates are available? Okay, it's not just one or the other. There are more to it. There is more to it than that. Let's create one ourselves, though. Okay, that's me. That's Rachel. We can make one because we've got this make a function code now. So I want to create a function called exclusive OR, XOR for short, which accepts a couple of Boolean operators. The first one called A, the next one called B. Done with that. Okay, how do I define XOR here? Well, this is simply going to return a value, and we've got that. So in my functions, I can return a value from this. And the return of A, XOR B, there's Boolean logic which gets us a way of doing this. And, you know, if it was working with a class, I'd make them struggle and think, can you come up with the truth table? But, you know, can you combine and OR gates in some way to create this? For you guys, I'm afraid I'm just going to actually just write the code here. And what we've got is a couple of things being anded together, and they're both ORs. I'm hoping I've got this right from memory. And another OR going in the other one. And the first thing we do, if A or B, then typically we're going to have 1 for the XOR. If A is true or B is true, then XOR is likely to be true unless both happen to be true. Now, how you get that taken out is to do the converse of that. So it's not A or not B. So our logic for that goes in like that. A and okay, so with a little bit of luck, okay, you know what's going to happen now. It's going to go horribly wrong. I should have working for me not an XOR gate of my own devising here. So here's my if, and we wanted point x1 and x0 and x1 should be okay. So I'm calling it with whatever those pixels are, whether they're lit or not lit. And if I've got my XOR definition correct, we should see an XOR coming out of this. So that's looking good so far. They're lit, so the XOR option is lit. If B is lit, that's lit as well. Moment of truth coming up now, because both of the 4 bits are going to be lit. We should get a blank at the bottom. There, blank at the bottom of the screen, because there's not one where it's one or the other. The only time when I've got that is when both are lit there. So, right, okay. So there we go. We've got an XOR working. Now, once you've got an XOR gate, this looks a lot like the sum of these two numbers. Let's put this back on here. So what we've got here going on, it's like the sum of these ignoring the carry. So I've got something going on about making some sort of addition thing, or I've got the rudiments of addition going on. So those two added together typically will give me the sum of the two numbers at the top. They won't always, because there's an issue with that, but there's a sense in which they're a bitwise sum of this. I need to worry though about the carry, because 1 and 0 is 1 plus 0 is 1, 0 plus 1 is 1. So XOR does that. 1 plus 1 is 0, carry the 1. And it's the carry the 1 that I've got to worry about next. So I'm going to need to do that as well if I'm wanting to do addition here. So let's see if we can figure that out. And naively, I might just go for something like an and here. So if they are both lit, 1 plus 1 is 0, carry the 1, then we'd be okay. So let's pop in, again, my call to the point, duplicate that. Pop that in there, duplicate this one, pop that in there. If those are lit, then my carry digit should be lit. So I need to duplicate that and pop some sort of carry row, just as, you know, if we're doing hand addition, then that goes up on the next column across. So that's not X4. I'm going to pop this upper row and actually move it across into the next column there. So let's do a little bit of math with that. Take away 1 to move to the left. X take away 1. And we're going to do the same sort of thing for unplotting LED. Unplot. Okay, duplicate that. This would have been quicker in the text-based language, but I would have, I'm sure, made loads of mistakes with the syntax, which is kind of the point, isn't it? So I've kind of got a sum and a carry going on here. Okay, let's see whether the carry happens. Yeah, okay, 1 plus 1 is 0. Carry the 1 here, but I should have a 1 down there for the next sum. So I need to extend this a little. I'm going to shrink this code to fit it better inside my browser window at this point. And I kind of need to nest the XORs at this point. Actually, I do need to nest the XORs at this point. So let's do one XOR inside another. And this time it's that carry point as well. So that's the LED point at wherever X is. And the carry row, which is row 3. So that should give me a proper addition. That should give me the proper sum. The carry is harder because there are loads of different ways the carry condition could be met. So you've got that one, which is the top 2 rows being lit. Then you've got the top row plus the carry row, or you've got the second row plus the carry row. We've got Boolean logic, which will sort that out for us, but it is a little bit painful here. It involves nesting a couple of OR gates, popping that one into the first of those. I'm going to duplicate that, pop that into the second of those. Running out of screen here, folks. Okay, duplicate that again, pop that into the third of those, and then finesse the detail here. So I've got row 0 and row 1. I want row 0 and row 3 for the carry, and I want row 1 and row 3 for the other possibility with the carry. That's a horrible nested OR statement, but if it's working, it's working. Okay, here we go. So by full adder, using the display on a microbit, we have got something in row A, we've got something coming up in row B. That, I don't know, is that something reasonable? Let's pop some more bits in there. So what have I got? I've got a 4 and a 2 and a 1. That makes 7. I've got an 8 and a 1. 7 and 9 is indeed 16, which is the bit pattern at bottom row there. And we have 51 seconds left by my clock. So from nothing to creating a full adder using the microbit pixel display as promised.
And that is so awesome. Like, oh my goodness, we are all gobsmacked. So hopefully you're going to share that link again.
I'll publish the new version of this. I don't even know whether it updates the version, but if you grab the code whilst you can, because you may not have access to the chat afterwards. But that's my version.
Exactly right.
There are ways to make this much more elegant, but I'll let you do that for yourselves. Okay,
that was amazing. I think everyone has enjoyed it. I'm just watching the chat and they're like, oh, watching the pressure build and the tension. It's exciting. Yeah, people are really enjoying it. So that's awesome. So thank you so much, Miles. And thank you everyone else for joining us for the last session. Can you believe we are at the last session? And there's going to be no break. Everyone's supposed to hustle over to the stage right now for the big finish. So thanks again, Miles. I hope everyone has their code now safely saved on their own computer, because that might be keeping me up
Bob, thank you so much for facilitating this, and thank you folks for joining in with the text chat there. I'll see you on the main stage.
Bye everyone.
Bye.